Okay, guys. Last time we stopped on the definition of isotopes, and we said the isotopes is different modifications of the same element found in nature due to the differences in the amount of neutrons found in those modifications. And we gave one of the examples here of those isotopes of a carbon. Carbon element here, if you look, atomic number is 6. Atomic mass or mass number is 12 point something. So if I look at the carbon here, carbon is as a symbol here. So that's a symbol of carbon, has, according to the periodic table, 6 and 12.01. This is, we said, atomic number. This is atomic mass or mass number. Sometimes just called mass number. So, and we want to see this one in nature. How does it really predicted in nature? So in nature, we have 3 types of modification of this element. So we have carbon 12, we have carbon 13, and we have carbon 14. So carbon 12 is by far the most abundant modification of carbon in nature. So the abundance here in percentage, as you see in the top here, and I put this one here for you here. The value here is this one here is 98.89%. The carbon 13, as you can see here, from this value here is 1.11 percentage. Okay, and here's almost 0%. So we have this is the way we can write the isotopes. Isotopes are written this way here. So say carbon 12, carbon 13, carbon 14. So that's the way we can express isotopes. Isotopes are written in the way you said, first the first element. That's the element itself. That's a dash, and that's the number of the atomic masses. All those are what? Atomic masses. Those are atomic mass. Now, when it comes to the atomic mass recorded in the periodic table will record the average weight atomic mass, not the natural real atomic average, but this is atomic weight. So we have to weigh in the abundance of each modification of each isotope of that element. So a periodic table boasts the average weight atomic mass. Okay, so let's look what we mean by average weight atomic mass. I'm taking this one out for once, twice, for the third time, for thrice. Okay, take it out. Okay, I'm taking this one out. Let's look at the this one here out too, so we can take this one here. No need for it. So now we will calculate for carbon. You can calculate for all elements if you know their isotopes. There is a big table there. You can Google it, and you have the chart there or table. Each element which is isotopes, and each isotope with its abundance. So for carbon, we have carbon 12. This is 98.89%. Carbon 13 is 1.11%, and carbon 14 is almost 0%. So the average weight atomic mass equal to, we have to weigh in. That's weigh means you have to weigh in the abundance found in nature. So will be equal to, correct? So the atomic mass here is 12, the first one, the first isotope, multiplied by 98.89% means over 100. This is isotope with atomic mass 12. Plus, this is 13 here. So we'll put 13 here. And the abundance of it in nature, 1.1 divided by 100. Plus the 14 here, atomic mass. However, this time is 0 here, 0 over 100. So if you look at the whole, if you do the whole equation, this is isotope number 13. This is isotope number or atomic mass 14. So we have, this is the average weight. You take the atomic mass of this isotope multiplied by its abundance. Of course, its abundance divided by 100. That's the 100%, correct? So when you calculate, this value here will be posted in the periodic table. Posted a value is posted in periodic table. So it should be 12 point something, 12.1, whatever in the periodic table. I can see it here, 12.02, not 01, 02. So let me take, and you can verify it if that's really true or not. You can verify that. So it said 0, 2, 1. Of course, you have to observe the 12, 0, 2, 1, and the units is AMU, atomic mass unit, or 12.021 gram per mole. This is the atomic mass recorded, which is coming from the calculation. You can verify it. It should come in the same thing. That's what we got according to their abundance in nature. Now, just to let you know, these isotopes with their modification, they have their own application in the real life. So the 12 here, carbon 12, this one here, that's the most abundant one. That will have the control. That will come always. When you have 12, then you know that in the periodic table has to have 12, because that's the most abundant. The most abundant isotope will control the outcome, correct? So this one here, the usage of it, this is our well-known, this is charcoal. So you can see that those are and this one here, the carbon 13 is used in analytical forensics. So those are the application of those isotopes. Carbon 13 used in called NMR. You heard about MRI, nuclear magnetic resonance, nuclear magnetic M resonance. MRI, the same thing, nuclear magnetic resonance as well. So the 14 here used for aging or age determination. So if I have a bone or a dead corpse, I want to know how many does this object, the dead object, is staying there in nature. I mean, buried inside the soil. So I use what? Carbon 14. Carbon 14 is a very good isotope to determine the age of, of the soil, of dead. Mostly it's dead bodies, usually for bones. and it's related to forensics as well, but it's mostly is for things happened in the past, like in the Greek Roman, they have a lot of old buildings, old corpse, whatever. So you can tell how many thousands of years that's age. So carbon 14 is used for that purpose. So we know now the periodic table is posting only the weight, average weight atomic mass, not the normal mass. So if you can come and tell me this is, and that's what the major students will do. What the most students will do? Well, what's the atomic mass? What's the average atomic mass of this? I'm not saying weight or weighing this the abundance. Give me the abundance, and some of the students what in the past are doing, they take 12, 13, 14, 12 plus 13 plus 14 divided by 3 isotopes. That's the normal real average, real average. That's a real average, but that's not recorded inside the periodic table. You have to be fair with the abundance. Not all of those isotopes are found in nature equally. Some of those are found in abundance. Some of them barely, like carbon 14 is there, not zero, really 0%, but 0 something. So something like this here. And this is, we say that's very minimum, but it's still there though, still there. Are you following me here? So by adding those atomic masses and divide them by the number of isotopes, that's correct if we are looking for the real average, normal real average. But we are not posting the real normal average inside the periodic table. We are having this average weight atomic mass posted inside periodic table. So that's the topic here. And any questions so far? Any questions? So I will go for the next one. The next topic is, now we know the atom and how is Rutherford done with that, how other scientists came and then discovered the neutron because of the atomic masses are not really correct. So they corrected the atomic mass by discovering the non-charged particle called neutron, correct? Neutron, has no charge, neutron. So now we have to know how we describe the motion and the behavior of those this atom with its electrons, correct? Remember, electrons are moving around the nucleus with the speed of light, but they are not localized in somewhere inside the atom. They are moving. But the only localized particles are neutrons and protons inside the nucleus. They don't move outside or moving around the electrons. Electrons are moving around the nucleus itself. So we have 4 quantum. You don't have to worry about that. That's not sorry. Quantum numbers describing the behavior of the. That will not come in the quiz or exam. That's higher chemistry. But I can't jump to the higher chemistry without giving you a little bit of the meaning of it. So those 4 quantum numbers are describing the atom itself and its behavior. So 1, 2, and 3, and here we have 4. So the first one here called principal quantum number. Principal quantum number. So QN. QNs, okay? So those are QNs, quantum numbers. This is number, correct? Quantum numbers. So principal quantum numbers is given to the symbol of small n. Okay, that describes this energy and distance. Energy plus distance, okay, of what? Of electron density from the nucleus. Of electrons from nucleus. The other one called angular quantum number. It describes the shape. So give us the shape of this electron density. Okay. So how their shapes when they are moving around the nucleus? What's the shape of those motion of those electrons? And the magnetic quantum number give us the orientation of this electron density, orientation of electron. When I say electron here, means electron density all the time. That's it's meant. Electron density from nucleus all the time, relating to the nucleus all the time from nucleus. So all the time it's always shape electron density moving around the nucleus itself. Number 4, called spin quantum number. That will give us the clockwise or anti-clockwise rotation of the electrons around the nucleus. So this spin here, we have clockwise and anti or counter clockwise, spinning around the nucleus, spinning around, always related to what? To the nucleus, around nucleus. So those are 4 ones, and if it's clockwise plus half, and you don't have to memorize this, I mean, it's just extra information for you, but at least clockwise is half, anti-clockwise minus half. So minus half plus half. So as I said, that's higher chemistry. You don't have to know them, but I would like to bring them for you so you can understand what's really describing this atom. Atom is described by those 4 quantum number that give us their orientation. I say all the time electron density because I cannot pinpoint or localize the electron around because they are moving speed of light. How in the world you freeze the electron and you measure the atomic radius or measure its speed? No, we are dealing with the electron density as whole, correct? And those 4 quantum numbers are really describing the whole thing. Energy, distance, shape of this electron, then electron density, spinning around the nucleus clockwise, counterclockwise, and the orientation, how they are oriented in space in relationship to the nucleus itself. Now, as I said, this is extra information. You don't have to worry about. But we are worried about the shapes. Well, we said the shape, first of all, the principal quantum number, just to tell you this principal quantum number, the symbol of it is N. The angular quantum number, the symbol of it's L. The magnetic quantum number is M subscript of L. And the spin quantum number is small s. This is small. Okay, guys? And again, you don't have to know this, but again, let me write it again. Here it is. This is energy here, plus distance. This is shape. This is orientation. This is plus half clockwise spinning minus half anti-clockwise spinning of electron density. So that's the symbols, and that's what they do. We are really interested in this because this is give us more. We are really interested in how those electrons are entering the orbitals and how they are really aligned up in those orbitals. Correct? So we'll look at the angular quantum number in some details, and we'll look at the radius a little bit. Magnetic and the spinning, that might be later on if you are interested going for higher chemistry, general chemistry, you will know more about those. So everybody has this? Everybody has this? If you can't catch me, because I want to move forward, so you can take snapshot of that. So use your phone to take snapshot of this. So, but it will be recorded anyway. So let's take this one out and look at the shape. The angular quantum number give us, we say, the shape. What are those shapes? So the angular Qn give us the shape, correct? Well, it turns out to be we have 4 shapes. That's what we have until now because we have 7 period. But if somebody will go another galaxy in million years from now, maybe we'll have more elements in that. Therefore, we might have something else. So we have S, B, D, F. S, B, D, F shapes. So S for spherical. This is symbol dumbbell. Here for complex dumbbell shape. And here is very complex dumbbell shape and shape here, and here is the shape. Okay, guys, so we have S, P, D, and F. Well, it turns out to be really F will be very complex even to visualize and to draw them. Those are 3D shapes, and it's very hard to be visualized in just plain 2D sheets or whiteboard. So I have a whiteboard which is 2D, X and Y. I don't have in my shape here of my sheet, the white sheet here. I don't have. I'm missing the Z-axis, correct? I don't have a Z-axis here. So it's really the shape of this whiteboard here is 2 dimensions. So let's look at this. So this one here, the electron density used to say the electron density is spherical. So that's a sphere. So the density is, and this is the nucleus here, guys. This nucleus. And the electron density here moving in a spherical way. So if I have this is my Z-axis, this is my X-axis, this is coming to me here, my Y-axis. So the nucleus where? This is my nucleus, correct? So nucleus is here, and those electrons as a whole density is moving in a spherical way around the nucleus. That's the S shape, correct? So since this is the S shape, we'll say this is S shape. Now we just elevate this one here, upgrade this S shape into what? S what? Orbital. or sometimes we say this is S shell. There's orbital shell. We exchange those, but there is a distinct between orbital and shell. There's a distinct one, correct? So S orbital and S um, shell. So that's, and the same thing, this P, we can say this one here, we can upgrade them as P orbital. And this D what? Orbital, and F orbitals. Okay, guys? So, can I take this one out? Everybody has it? Take a snapshot of it? Everybody has it? Okay, so I can tell you now how those shapes are really looking like. So I have S will be looking like this. This is S orbital, correct? Then I have this B orbital. It has, because we have the 3 dimensions, correct? It has Px, Py, and Pz. So if I have here is the nucleus here, guys. And here's my nucleus. This is my x-axis, z-axis, y-axis. Then I have here, guys, look at this. This is this called here Pz. That's here, the Pz orbital. This is Pz orbital. It's really not really orbital. This is just a suborbital. It's a suborbital because the whole orbitals are made of, the p orbital made of 3 of those. 1, 2, 3. This is the same thing, px suborbital. And this is the px will come. Let me just write it here, guys. You don't have, that will not come in the exam or something like this. It will not come. So let's take the violet here. This is the px. And then the last one here, maybe take the orange one. The orange one will come. And this is py suborbitals. Okay, guys? So if I have a p orbital, then the p orbital is divided in 3 equal suborbitals. Px, Py, Pz. And that's type of drawing, we call it orbital diagram. Orbital what? Diagram. So, are you following? So that's, we call it orbital diagram. And furthermore, when we enter those electrons, we enter them as arrows. So arrow up, arrow up, arrow up. Those arrows are electrons. Okay? Up means they're spinning clockwise. Down is counterclockwise or anti-clockwise. Spin around the nucleus, spin. Okay, guys? So now we know that the s orbital is straightforward, just a sphere. They move the whole electron density, the whole bunch of electrons are moving in a spherical way, like the whole planets around the sun. All those planets, including the Earth, our Earth here, is moving around the sun in a spherical way. In what spherical way? So that's what s orbital is. The p orbital, however, is in a complex, is one orbital, but it has 3 suborbitals, depending on the dimension and orientation of each suborbital. So this dumbbell is around the z-axis, that's the Bz or suborbital. On the x-axis, Bx orbital, suborbital, and the Py suborbitals. Now, any question about this? Again, you don't have to memorize this, but you have to know about those orbitals and the orbital diagram, and this arrow means 1 electron, up means plus Up means clockwise means would be plus half, and counterclockwise minus half. So it means if this is the nucleus, the electron spinning like this way. Some of them they spin the opposite way. So depending what they are in. Okay, guys. So let's take this one out. How about d orbital? The f orbital I can't really. It's very complex. Very complex. You cannot do 3D in a 2D with the f orbital. But the d orbitals, well, the d orbital here turns out to be d orbital. It has 5. Remember the p orbital 3 sub. This one 1, 2, 3, 4, 5. 1. So it has 5. 1, 2, 3, 4, 5. What they are? They are dz square, dx square minus y square. Okay, and then you have dxy, dxz, dyz. So you have 5 suborbitals. Okay, you can name them whatever, 1, 2, as 3, 4, 5, and that's what they go here. Are you following me here? Now, drawing them is not really difficult, but the z orbital is like this one here. This is the z. This is your y. This is your x. And if you look like this, it's a dumbbell here, and then inside dumbbell there's like a donuts. They spin like a donut, so they go up, 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 and then donuts in a spherical way. So, as I said, you don't have to memorize this. The x and y, those are in between. I mean, on the axis, x and y. This is x here. This is z. This is x. This is y. So they come here, here, and then y is here, here. X, y in between. Y is in between those. That's x, x, y, y. So you don't have to memorize this, but at least the orbital is made of 5 subshells, 5 orbitals, 5 orbitals, 5 suborbitals. So 5, and those are here. Do we have to memorize them? The answer is no. And just look at the whole thing here. Now, can I take this one out? And as I said, you will not be asked, even if you go higher chemistry, nobody can, because it's very, very hard to draw those 3Ds in 2D dimension. So just to give you a hint of this, here they are. Let me make it bigger so you can see it here. Can you see that? So, and you can see there is a YouTube link in your PowerPoint and your eBook. So this is the s orbital here. I can go through them here one by one, but at least you get the idea. This is the s orbital here. Again, this is the z. This is your y. This is your x. Okay, so axis, and the nucleus is here in the middle. Here's the nucleus. 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 How many the d orbital has? 5. How many p? 3. How many s? 1. So if I make it smaller, then you can see they don't really give them the names of that. So they should really name them the bx, the by, bz. So if I go here and say to myself, okay, let's take this one out and say take this one out here. And take this one out here. And I say the SBDF orbital images. And if you Google this, and here you are, you will see all the, it is very nice. Let's do this one here. And if you can see here, bless you. So here they are. That's the BX, BY, BZ we talked about. Don't worry about that. So take them, they will come back. But anyway, so that's the, you can see those here. I can make them bigger, but this is the BX, BY, BZ. And when it comes to the other one here, you can see that's DXY, X, XY, XZ, DZ square, like a dumbbell and then a donut between. So you can see them here. Now, the F shape, don't worry about it. It's very hard to visualize. It's very hard to visualize. So if we have an F orbital here, I can show you maybe this picture here. Okay, so you can see how complex the F have 7 suborbitals. How many? 7. So let's put this one here as a reference here. So this one here, S orbital here, has only 1. Okay, one orbital. This has 3 orbitals. This one has 5. This is the d orbital D, and this is the P. This is the S, and the F has how many? How many? 7 orbitals. So you can see the F is so. I mean, I can't. I tried to draw them, but it's very hard to draw. And those are drawn by a computer software, so not by artists, but by computer software. So, but anyway, so you get the idea. That's the shape, how they spin around one. And your coordinates, 0, 0 coordinates, that's your nucleus. That's the nucleus is there. And those are motion of electron density moving, correct? So, as I said, you don't have to worry about, there's nothing there. But we have to look at the electron, how those electrons are coming into those orbitals and organized in a way that they have no friction or no problem with their motion against each other, correct? That's very important for us. For this one here, then we have the table here. We can see a table here. We can take a table here and make a table here, guys. So it is. Let's make a table together. Let's make a table here. We'll see. This is a table. Let's put the table here like this. Okay, like this. So, and we'll take n equal 1. Now n is we said the principal quantum number, correct? But n in this sense is number of the period. So when I say n is really number of the period. So n is number of the period itself. So n is number of this one here, number of the period in the periodic table. Number of the period, which is the main quantum number, principal quantum number. N2, period 2, N3, N4, N5, N6, and 7. You have 7 period. This is 7 here, guys. So then what we have S, correct, orbital. This is S. This is P. This is D. This is F orbital. Okay, so we can take the other one here. And here is number of sub orbitals. We'll see how much they are. Okay, n is number of the period, correct? Number of the period or principal quantum number. Principal quantum number, n. It's the same thing, number of the period. So if you look at this, the first orbital, the first period, we have one s. We don't have two s. The second one, we have two s. Remember, 2 is always number of the period, number of the principal quantum number, and 2p. So we don't have those here. So the one orbital is 1. Here we have 2, correct? Then NP and 3, we have 3s, 3p, 3d, no f. So how many suborbitals? 3, correct? 4 then, now we have 4s, 4p, 4d, 4f. We have 4 here. In the fifth, we have 5s, 5b, 5d, 5f. This is 4. 6s, 6p, 6d, 6f. This is 4. 7s, 7p, 7d, 7f, and this is 4. Now, if we have more than 7 period, we might have after f will be g. If we have n period, eighth period, we have 7. We have 7 columns called groups. Now in the old one, and this one here is 18 groups in the new one. In the old one is 8 A's main groups and 8B transition groups. But anyway, so we are looking at the periods here. So now I want to see how I enter those electrons. So I will do here, we call this one here head, this method called head and tail arrow, head and tail, here double R. So we are looking at the method called infilling those electrons inside their designated orbital. So I will go with the arrow here, maybe another color. Yeah, red is a good one. So this is the arrow, correct? So I make the arrows here. There's none here, correct? So this is the head of the arrow, correct? Now I'll come with the tail of the arrow. I come back and take this one here. Come back from the head to the tail, second one. So we'll start with the 1s, correct? The arrow goes all the way, correct? So it is from here. So this will start with 1s. After 1s will come what? We go up through, will be 2s, correct guys? And then go through 2s, goes all the way 2p, correct? Go back all the way 3s. I'm going here 2p, 3s, go back all the way here 3b, 4s, 3b, 4s, and then I come here 3d, 4p, then go 5s, from 5s all the way to 4d, 4d, and then 5p, 6s. Now we can stop here because that's up to the to the fourth and the fifth. We will not have elements in the fifth, but we'll go by the four. For if you go higher chemistry, then you will have all of them. But we'll stop here. But we can follow the whole thing. Just hold on. So can I take this one here? I'll show you one inside your hold on. Just hold on. I'll show you inside your PowerPoint, which is that's what I wanted to print out. The one here. This one here printed out, and maybe I'll copy it, and then I'll try to then let me just hold on. Let me make it smaller here. Okay. Yeah. So what's your question? Yes. What's that? Yes, you have to print something like this. That's in PowerPoint. That will come because you have to fill in those electrons, correct? So look at this. You need something like this. You need to print something like it. Take it from the PowerPoint, copy and paste into Word format, Microsoft Word file. Make it bigger, and then you can print it. You can follow the whole thing. Now, we'll do an example here. Okay, I'll take a simple one, and then we can take whatever we have. Always goes by the number of electrons, atomic number. So we are looking at atomic numbers, not atomic mass, atomic number. Let's take, for example, I will take first simple one, calcium. What's the atomic number of calcium? How many? 20. Don't worry about this 40, the atomic mass. We are interested in this. So we have to accommodate 40 electrons into their orbitals, correct? So how we do that? So let's look. We start with 1s, correct? I'm going to arrow down, and then the bottom, the tail of the next one, correct? So 1s, and I have to know another rule here, guys. Another rule tell me S maximum of electrons number is 2, correct? We'll see why it's 2. P maximum of electrons is 6. D maximum of electron 10. And F is maximum number of electrons is 14. So we have 14, 10, 6, and 2. Correct, guys? That's because the Pauli exclusion principle says each orbital can have maximum of 2. Okay, we'll look into this in a minute in those two Pauli and Hund rules. How to get those electrons fitting in. But for the time being, let's take this as a rule. S orbital, they have maximum of 2. So let's do this one here. So S2, maximum of 2. After 2 here, S will come 2S, maximum of 2. Correct? Go back. 2P, maximum of 6. Now I count until now I have here 6, 2, and 2. Those 10, correct? Now I have to go further. 3S2, that's 12. Correct? Is this following? 1S2, 2S2, 2P6. That's 10, and 3S2 is what? 3S2 is 12, and 3P6. I come here to B, 36, come back, and then what? 6 here, And then 4s, how much? How much left of the 20? 10, 12, 12, 18. This is 2. So the electron configuration of calcium, electron configuration of calcium is 1s2, 2s2, 2p6, and 3s2, 3p6, and 4s2. Okay, to calculate them, those have to add up. This is 2 here. They have to add up to 20. So you have this, this, and this, and this, and this. Those are the 20 here electrons, and this is the atomic number of electrons, equal number of protons, but we are interested in the electrons, correct? So that's the way those are coming in. Are you following me here? Now let's take another one. Can I take this one out? Okay, let's take something more. Let's take bromine. Let's take bromine. It has more, bromine has more electrons. So bromine has more electrons, so 35 electrons. So this one here, we accommodated how many? 20. Let's accommodate 35. See how does it work. So let's take this one out. And you just help me now. I pretend I have no clue what's going on. So what's starting with? What will be the start? We are looking at bromine. Bromine has, we have to accommodate 35. Atomic number is 35, which is number of protons. But we are not interested in number of protons. We are interested in number of electrons. So bromine 35. We have to accommodate 35 electrons, correct? So start 1, starting here. 1s2, maximum 2. 2, after that you come here. 2s2, come here. 2p6 maximum. After that 3s2. After that will come 3p6, 4s2. When it goes through, then you have to take those orbitals. So then the next one will be 3d, 4p, 5s, correct? So 4s would come then, 3d, maximum of 10, and 4p, how many left from the 35? Somebody had calculated? How many? Come on, guys, don't let me down. How many left? How many? 6? Come on, man. You should calculate 2 plus 2. Yes, 5. Correct? Calculate here. 6, 2, 6, 2, 10, and 5. Those are electron configuration of bromine. Make sense? Yes, no? Why not? Okay. Let's pick up one of the elements in the fourth period. Fourth period start with potassium 19 and end up with krypton 36. So pick up one of those. Those are the difficult. We'll not go for the other one. It's easy. I mean, you have to go through this arrow, head, and then the tail, head, tail, head, tail, head, tail, and then organize them. Okay, guys? What's that? Krypton, that's should be not difficult. Krypton, how many? So I'll copy the whole thing from the bromine, correct? Just copy from the bromine. So 1s2, 2s2, 2p6, 3s2, 3p6 from here, 3p, 6. After that, what will come? Let's put the 6 there. So you tell me what's next. 3b6. After that, what? 4s what? 2. After that, 3 what? 3d maximum of 10. After that, 4b what? 6. Can we stop here? Yes. Can we stop here? Yes, that's 36. Calculate them. Calculate them. Are those 36? Yes. So now this type here we have to transfer them into this called what? This called SBDF electron configuration. So this type of writing, we call this one here, guys. We call this one here SBDF electron configuration. So configuration. Now, can I take this one out? Okay, I'm taking this one out and then see what other type of electron configuration I have. Well, it turns out to be, I'm taking this one here as well out, so no need for it now. Now we have 3 types of electron configuration. 3 types of electron configuration. So 3 types of electron configuration. So the first one called SBDF electron config. Okay, guys. And the second one, if we have SBDF, we can have the orbital diagram. Orbital diagram, electron config. And the third one may be confusing. It's noble gas core electron config. 3 of those. So if I not want to take krypton, we took krypton. Can we take another one? Another one. How about anything? Yeah, but up to the 4th. We can't take the whole thing. But so which one? Which one you like? Up to the 4th period. Which one? Which one? Manganese. Okay. Okay, manganese. Here it is, guys. Mn. Manganese. What is the atomic number of manganese is what? 25. Oops, sorry. 25. Okay. So we have to accommodate how many? 25, correct? That's not one to take. Well, we'll say here, we'll write it just here. 25 electrons we have to accommodate. So the SPDF, that we start with, that's easy. This will be, you tell me now, you have the whole thing, 1s2, 2s2, 2p what? 6. After that, 3s2, 3p6. So how much we have now? How much? How much do we have now? 10 and 8, 18, correct? And after 3b will come what? 3b6. 3b will come what? 4s2. You can look it up. And then 3d what? So how much left now from the 25? How much? This is, calculate those. Come on, guys. Don't let me down. 5 more. It's not Monday today, correct? 5 more. So It's not Monday today, so Monday I can excuse you, but no excuse. So that's this 5 here. So this is called the SBDF electron configuration. This is called here SBDF electron config. That's the first type. The second type, the orbital diagram. Well, that's too long to this. I will do the noble gas. Okay. I mean, we can draw the electron orbital diagram means use boxes. Boxes equal what? Orbitals. And arrows equal electrons. That's like drawing. Arrows equal electrons. Well, this is time consuming. So I will go first for this one here. I say, how about the noble configuration? Can I use it? Yes. I go for the manganese. Where is manganese is? Manganese is in the 4th period. Correct? I go from the 4th period all the way to the end of it. End of 4th period, which is the noble gas krypton. I go one up. 1 period up. 1 period up. This is argon. How much is argon? Look, 18. So I say, well, that would save me a lot of headache, a lot of work. So 18. So I have, so well, then I can take those 2 and 2, correct? 2 and 2 and 2, 10, 12, 18. So I can eliminate all those out. I don't need them. I will write in this, the noble gas, this is argon. This is 18. What left me is 4H2, 3D5. 3D5. This is noble gas core, because this is 18 here. This is 18. You don't have to write 18, but that's for yourself to count the number of electrons. 4S2 3D5, that's a noble gas core. Now, orbital diagram will come easy to me. I can do what? I can do argon here, and then do boxes. The S is one box. It has up, one down, correct? And the D, this is for S2. Each electron with each arrow, one arrow, it represents 1 electron. So 1 up, they have to be different spin. And I'll call spins. The D, however, has how many? 5. D has 5. So I put here 1, 2, 3, 4, 5. So 1 up, when you enter them up, 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 up. And this will be 3D5. This is orbital diagram boxes and arrows, correct? And this is noble gas electron configuration, correct? So what's really controlling this is 2 rules. One rule called can I take this one out? Okay, one rule called the Pauli exclusion principle. 2 rules controlling this. 2 rules. So one is Pauli's exclusion principle or rule, and the second one is the Hund's rule. So those are 2 rules. What Pauli said, he said first, that's his condition, is each orbital has to be occupied maximum of what? 2 electrons. So 1, each orbital will have max 2 electrons only. You cannot have 3. Number 2, if you have 2, they have to have different spin. One will spin plus half clockwise, one will spin counterclockwise. So the two electrons have to have different spin, different spin, one up, one down. Hund's rule will tell you the same thing, whatever Pauli's rule is, will tell you, well, when you enter those electrons, you have to enter them singly and parallel to each other. So enter electrons here, all electrons enter, all electrons are enter electrons here. Let me just, electrons are entering, electrons enter orbital singly. Number two, when they enter singly, they have to be parallel to each other and enter parallel to each other. Now we had, let's take maybe fluorine. Yeah, fluorine. So let's take fluorine. Can I take some of those rule out? Can I take them out? Let's look at the application. You don't have to memorize them. I need to see the application of them. Can I take this one out? So let's take example here again. Fluorine. What's the atomic number? Now we are not interested in atomic mass. Atomic number. How many we have to accommodate? How many electrons? No, 17. That's atomic mass, correct? Fluorine, I said, not chlorine. How much? How much? 9. Let's look at the fluorine. That's 9. Atomic number 9. Not the chlorine. Chlorine is you said 19, so 17. So 9. So what's the SBDF? SBDF electron config is? What is that? The first one? Come on, guys. 1s2, 2s2, 2p what? 6, 3s what? 2, 3p what? Now we have over 10. That's wrong. I can't tell that's somebody sleeping on me here. I can't put 3 because this is in the fluorine in the second period, so it had to stop here. So the 6 is not correct. What should we write in the 6? 5. We have to shoot 5. So well, looks like Monday today. So that's SBDF electron configuration. I need to get the noble gas core electron config. So what should I do? I go all the way. What's period in? Number 2, second period, correct? Second period, I go all the way to the end. Enter it. End second period, correct? What's the end second period? What noble gas is there? Neon. I go what? 1 up. Will be helium. Helium. So helium how much? What is the, it has 2, correct? Helium is 2. So therefore I can eliminate this. I said this is helium because it has 2 electrons and 2s2, 2p5. This is noble gas electron configuration. How about the orbital diagram? Orbital diagram. So I say, okay, I keep the helium as is, that's 2. I have to have 2s, 2, so I have 1 up, 1 down, according to Pauli. 1 up, 1 down. I can't put them both the same thing. And the second one is P made of 3, 1, 2, 3, correct? Px, Py, Pz. So I have 5. So according to Hund's, they have to enter singly and parallel. Parallel means they have the same spin. Up, 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 or down, down, down. 3. Then the opposite has to be the opposite. You cannot tap this. That's 4, and then 5. And this is 2p 5. This is the electron, the orbital diagram, correct? Now, let me see if you can really visualize this quick, and then we'll go for the last 4 minutes for the diagram here we can see. So here it is. Can I take this one out? Take this one out. Let's take it out. It has it. So let's look at this is boron. Boron has 5. You can see, correct? And you can see oxygen, nitrogen has. See how nice they are there. But sometimes they can trick you and then give you the opposite of. So they can give you opposite. So look at this here. That's incorrect. That's incorrect. See here? They have to enter. See here, guys, look. They have to enter what? Singly. In each orbital, suborbital. Each singly. Not combine themselves in one. No. They have to enter according to Hund's singly. And parallel to each other. Parallel means they have the same spin. Okay. So that will end up this electron configuration. If you have doubt about this or need extra help, just let me know. I'll be more than happy to help. And we'll go for the last thing here, the last diagram here, which is this one here. Now, guys, look at this, guys. Still we have 4 minutes. We'll look it down. We have 4 minutes. Come on, guys. We have still 4 minutes. We have to go to 4 minutes over this. Now, you don't have to memorize what's really ionization energy is. But ionization energy is, I'll first explain atomic radius. Atomic radius. Well, atomic radius is not the distance between electron and the nucleus. Atomic radius is the distance between two adjacent nuclei. So I have this distance here. Two nuclei, the distance between them, this is A, this is P or A. This is between two nuclei, the distance between two nuclei called radius. This is radius here, atomic radius. Okay? And ionization energy is the ability of an atom. Ionization energy is the ability of an atom. So if you have to ability, if I have aluminum here in the gas phase, so you will see aluminum can, it has three electrons, correct? 3 valence electrons. We'll come back maybe Monday, we'll look at this, but aluminum can give away all its electrons. Can give away all its, so this one here can give another electron here, 2 plus 1 electron, and the L2 plus can give you Al 3 plus 1 electron. So the ability of electron to give away its valence electrons. Valence electrons are electrons found at the outermost orbital. Orbital that's found in the outermost shell or outermost orbital. So we have what we have fluorine, 1s2, 2s2, 2p. That's second, correct? And we said it has how much? It has 9, correct? And this has 5. Now, the outermost is 2, second orbital. So this is 2s2, 2p, 5. I have 7 orbitals, which is the number of the group. This is called valence electrons. Valence what? Electrons. Valence electrons, and this is called here outermost, last shell, last orbital. And I have how many? 7 electrons, 2 and 7. Why 7? Because 2 here and 2 here, that's second orbital is the last orbital. The second orbital And this is the last orbital. So I can say, oh, it's 46. I'll stop and then I'll show you the quiz is in what in Wednesday, correct? Next Wednesday. So Monday I will go through this again to this diagram. Okay, and go chapter 3.